So, guys, today I wanted to show some basic structures of our university level studies, and I want to share some of the concepts that's actually pretty easy for us, but in our schools and colleges, it's not taught very easily, and also that's why in the university we do not feel very confident regarding these topics. So, I wanted to share a few of my experience that I had regarding this so that the new students can feel very much confident about it. So, physics is quite an easy subject for is the easiest one. So, the basic structures of the physics consist of thermodynamics, which is the very basic structure and almost the fundamental, and then comes work and energy, which is quite essential. Gravitation, the laws and forces regarding the gravity that occurs for different mechanisms and machineries is quite does play quite an important role in our day-to-day life. So that's pretty much important. Then comes oscillation, which is a form that is very important because the energy fluctuates, energy goes up and down, right? We can see that in our day-to-day life every now and then. Waves come as a part of it. So waves and oscillations and the energy, quite important part of us. Then current is very important. We're going to talk about all of them one by one. So we're just starting with few of the items that we have. Current, mostly alternative and direct, which plays a very vital role in our life because we have to transfer the electricity from one location to another, and from there it supplies all the doors, all the homes. And very important topic, electrostatics, because electricity we use in our day-to-day life, and we have to know the ways we are using it, how we are charging, the power supplies are coming, how the electricity moves from the circuits, from the wires to different components and charges up, how the atoms comes in this regard, very important. So I cannot create a 3D model quite much. Atoms are very important. That's how the electricity works. Flow of electron, not exactly flow of. It's just a movement. We think it to be the flow. However, it does charge up our devices. Our day-to-day activities depend on the electricity. That's the modern life. And comes kinematics, which is almost dependent on the other topic, which comes on with the motion. One is kinetics and one is the conservation law works out. It does balance it out. So if our kinetic energy is the highest, our energy, the potential we got as a momentum stays low, which is quite legit and understandable. And when the kinetic energy is the lowest, the other form of energy stays the highest. So it's pretty much a property of physics. So properties of matter is a very important topic. How the matters work, how the matters react, how the matters bond. Then comes wave optics, right? Because that's how the light does move. Law of motion, how the collisions and the physics work in terms of aviation and vehicles and different machineries or mechanisms or mechanical parts we use. It depends quite much on the laws of it. Work, energy, and power. It's quite important. I'm not going to be able to cover all of them in one sitting, I guess, because it's quite some vast topics to cover. Work, energy, and power, we could call it force as well, because those all of them are important. Comes up with motion of, I take it up, ears. So the things that we're coming up with comes a system of particles. So what do I mean by particles? What sort of particles are there? There are currently 4 or 5 types of particles. Major particles starts with 3. So if you think in the perspective of the universe, there are a lot of particles. But if we think in our in this world, in our world, then we can stay limited to a few of the particles, and I think that's okay. We don't need to go further. Let's finish it, and we'll cover those topics. Then units and measurements. It's just a very basic topic. You don't need to be very big, right? Because this is quite basic. Like, you need to know it as a kid, so it really shouldn't be focusing that much on this at this level. Motion we talked about it before. Force, we talked about it in right. So force is a very fundamental part of physics. The way the laws of forces are very important. The 3 crucial laws that is the basic of our world. Any part of the world we go, we have to follow the basics of this. So 3 of them are the 3 major rules of forces, that when the forces we push, we get the same amount of force. The amount of force we push actually converts the same amount to the other object. And the other one is force is conservative. So whatever the force we preserve stays the same. It just changes the way and changes the forms. So quite much in a similar topic. So very important. Aviation is part of physics. That's how the modern day warfares are being run. That's how the modern vehicles, the super cool tech vehicles we see, they're all based on the laws of basics that we all need to learn, so we know how this works and how those are created, which is very fun. For me personally, it's very fun. So the people who feel interested, do definitely look into it. The other, so straight line, vector ways, we can go here and here to this direction, to this direction. Straight line, not a straight line. So the straight line motion and the vector type, that we change our direction. It's not a straight line. You can call it curvature at some points as well, but it's not a proper form. Straight line motion is more preferable, and mostly we do follow the rules for the straight lines, and we do design our vehicles or our day-to-day activity machineries according to the straight line, because straight line is the shortest line, is the shortest way. And comes electromagnetic wave. This is a very interesting topic, one of my favorite topics of once. So how the electromagnetic waves work? See, we feel two axes. This is x-axis, this is y-axis. But we can think in 3D. In that case, we are considering this to be the z-axis. So, say our electromagnetic wave, some radiations do have both electric and magnetic radiation. So what it means, as well as electric, so it does create electric radiation. So you'll feel, if there's a positive charge, it would feel attracted to a negative charge. So if it radiates the positive charges, the negative charge would feel the presence of it because it's going to feel attracted, and it does have a magnetic radiation at the same time, which is quite impressive, I'd say. So what happens in electromagnetic waves? The electric radiation, if it goes in the x-axis, say this is the y-axis, sometimes in the z-axis, or probably, yeah, so this is a 3D model. So if I put x-axis in this way, we can count these to be a z-axis. This is 3D, so the drawing wouldn't be perfect. So say this is the electric wave, and the blank spot is a magnetic wave. So what happens in the electromagnetic wave? It goes together similarly and does attract the opposite materials. Say you're plus, you'd attract minus. If it's magnetic poles, positive pole, you'd attract the negative pole. So it's quite fun, and it does follow the basic rules of physics, that it goes say E1, E2 in proportion to, and then divided by d squared. So it does increase the amount of force or amount of its radiation along with the power is generating, and the electric power, how big the proton or positive charge is, or how big the magnetic charge is. It's quite fun, and the farther it goes, the less force it has. It's just normal. We'd feel much more attraction or force when you're closer to it. So the topics are pretty simple. Nothing pretty much. So we erase all of it. So let's talk about it one by one. It's pretty simple. I'm gonna make the video very, very simple in here, and then later on, if required, I will make full videos on it. But the basic rules, for the people to feel interested. That's the most important part. If we do not feel interested towards it, then we do not know how to utilize it, how to implement these laws in our daily or every part of our life. So in our day-to-day use. So we see physics everywhere, right? The cars we ride are done with physics. So we have to know the law so we feel interested and make it count. If we know how to utilize the laws of physics and how to make our physics go more advanced, we have to learn it, and then we'd be able to think about it because we already have the knowledge about the current physics. We would be able to develop our tech, develop our device, develop our vehicles, develop our transport, develop our aeroplane, aviation, develop our technology of speed. So it's everywhere. So that's why we need to feel interested. We want to make our tech go higher, advanced. So thermodynamics is pretty. Actually even very young people can understand it. They don't need to be in the level of uni to get to know about it. Thermodynamics. I start with dynamics. What are the laws of it? Say we have an ice cube, right? And we are keeping the ice cube in water, right? Basic enough. The ice cube is gonna melt and it's gonna get to the same temperature as the water, which was at say 4 degrees Celsius, and the cube was at 0 degrees Celsius. So what does it mean? All the particles come to the same exact temperature if it's together. Say X material, which is pretty hot, like high temperature, is kept high temperature. Alright, kept with Y material, which is low temperature, like say 0 degrees Celsius, and this is 10 degrees Celsius. So after some time, both are gonna be 5 degrees Celsius or closer to that, but both are gonna be at the same temperature if you keep it in the same place and the same temperature. So that's quite thermodynamics. Nothing much to learn about it. There are three basic scales we use. One is says Celsius, is Fahrenheit, Kelvin, which is quite much used in the scientific measurements, because Kelvin is a scale that stays quite the same. Say Celsius and Fahrenheit, we have to increase it. Say when you see someone's body temperature is quite 36.4 degrees Celsius, which is 98 degree Fahrenheit. But when we increase it by 1 degree Celsius, the Fahrenheit temperature goes much higher, because the Fahrenheit is quite sensitive, I'd say. But in the Kelvin scale, whatever the scale was previously, if it was on, say, that's 36.4 degrees Celsius. So if it was on, say, X Kelvin, and if you increase the temperature by 1 degree Celsius, the Fahrenheit is gonna be quite much 2, 3 of increase, but the Kelvin is gonna be increased by 1 unit, which is exactly the same number of Celsius, which is quite much we have used already in our day-to-day activities. So known to us, Kelvin, easy, and easy to go up and down. And say 0 degrees Celsius, the Fahrenheit is not 0, it's 32. But the Kelvin scale, 273. So it is called the zero, the quite zero, because in this temperature everything freezes, and below 0 degree we can think ourselves up to minus 273 quite much, or not exactly, minus 273 degrees Celsius. This is the lowest temperature human could imagine in terms of the gas, because the gas molecules are all around us. So what are the percentages of different gas? Nitrogen, say 78%. Oxygen is 23% or something. Not 23%, it would be much higher, right? So let's say 21%. So the 2% is the rest of the gases. So gases all around us. So when we feel cold outside, so the temperature is low, our gas is low temperature. We have seen 0 degrees Celsius in water in liquid form because we can easily feel it. When it's 0 degrees Celsius, it's turning from water to ice. When it's below 0 degrees Celsius, it turns to ice. Pretty simple. So same goes for the gas. The gases are in such a way it doesn't get to freezing point so easily. So this is a freezing point of water. Gases are different molecules. Water is H2O, which is hydrogen oxide. 2 hydrogen, 1 oxygen. So say for nitrogen, it's different. Nitrogen also does have liquid form and also does have the same solid form, but solid forms are very low, so we have to go very down till minus 273 degrees Celsius to get to the lowest temperature to measure the. Till now, we could find out minus 273 degrees Celsius to be the lowest temperature because we can't go below that. All the gas we have found does freeze by 273 degrees Celsius, and see, when the gases freeze, we have nothing left actually. So there are no existence, there's no gas, there's no existence of any particle, so there's no existence of anything. So we cannot technically, according to the books, theoretically go below minus 273 degrees. If there's another universe, we discover they have lower temperatures. That's fine. That's a new discovery. Now, we have to go farther beyond our universe to discover that. That's a different topic. So, theoretically, this is our limitations. We use Celsius, Fahrenheit, and Kelvin. Among them, Kelvin and Celsius is more useful. And we use it, Fahrenheit, we use it while say we have to take measurement of our body temperature. We do it in Fahrenheit, but Kelvin is universally accepted with the people for the scientific researchers, because I show the equation that works towards it. C by 5 F minus 32 by 9 equals K minus 273 by 5. So how it works? So normally it says 100, it says 180, and it says 100. So we divided 100 divided by 20 is 5, 180 becomes 9, 100 by becomes 5. So our lowest temperature is if we count in Celsius, Fahrenheit, and Kelvin, say 0 degree is 32 degree Fahrenheit and 273 Kelvin, and 100 degrees Celsius when the water becomes vapor is quite much. 32 plus 180 becomes 212 degree Fahrenheit, and this becomes 373 at the same scale, at the same temperature, just different scales. So that's where the equation comes up to convert from one scale to another. In C and K, the division is by 5. So when we're using these two, we just add 273 to Celsius, we get the Kelvin. Quite easy, quite simple. So that's why we use Kelvin more often. Let's clear it up for the next interesting parts. So we're talking about thermodynamics a little bit. Say refrigerator. Pretty interesting. We have a small refrigerator. One is for normal temperature, and the other door is for the negative temperature, for the freezing temperature. What happens in refrigerator? So entropy is a part of thermodynamics in terms of everything wants to get back to a certain position. Yes, the light's back. How does it work? It's quite fun. See the order of our universe. So this is x, x, x. This is y, y, y. So if we put x and y together, it does want to get back to the form. So in that way, what happens? What is entropy? Is everything wants to get back to its previous form, its normal natural form. That's what entropy is. It keeps happening. Same happens for thermodynamics. What happens? We want to keep our fridge cool. That's why we radiate heat to the outside temperature. And inside, what do? We conserve energy by keeping the inside cool. How do we do it? We suck heat from inside and get them out. We absorb heat from inside and get them out. What's happening in this term? The world is getting hotter? A little bit, not much. But our foods and some places are staying cool, which is not the normal temperature. Normal temperature of the world is pretty high. Not near as the freezing temperature of a fridge. So in this case, the refrigerator plays a vital role to make ourselves clarified about knowing the laws of physics regarding entropy, because everything wants to get back to its position, and that's how the entropy of the world is increasing. So, and someday the entropy is gonna be either to the highest point, so the whole world or the universe is gonna be quite organized. But in that system, it would be hard to get the items back to its previous position. What would happen? Say we release some heat from X position or to Y position, or in position to out position. So getting the heat back into in, we have to put the same amount of work to get it back in. So yeah, entropy is increasing, quite fun, but at the same time, we have to get them back. Anyways, that's not part of our topic. To make things go interesting, it's all been some time. Work. Yeah, thermodynamics is pretty easy. The laws of physics. The temperature passes from one to another and comes to the same temperature. One important form. Say we turn on the air cooler. Alright, in our home, the outside temperature, say, is 36 degree Celsius, which is not, say, not too much. Right now, I'd say the temperature, say 20 degrees Celsius. And inside, I want to make it a little cooler, say 15 or say 12. 12 much. 15 degrees Celsius. For some reason, someone liked it. What's happening here? When you open the door, so this is our room. This is outside. When you open the door, normally we might think that the cold air probably is going to come out, but that's not what happens. Normally, in thermodynamics, say this is higher temperature and this is lower temperature. So the heat passes from the higher to lower. So when you open the door, even though the air might go out, the heat always goes from higher temperature to lower temperature, and the room would keep getting hotter until it becomes the regular temperature of the environment. Pretty easy, simple. Basics, remember it. Don't put efforts to remember that much. Pretty important. Important part is to know the basic things, to have basic knowledge, and to have common common sense, common knowledge, so we can figure out what way is going and what is the smartest way. What is the shortest way? That's the basic of physics. See, all the modern technologies we are using and we're gonna be creating. Say our day-to-day life is gonna get easier. Say vehicles, or say aerodynamics, or aviation. Say planes. We're gonna use planes someday. We're gonna use planes. That's gonna be much more cost effective because we don't put much on journey. We want to make plane journeys more available and much effective and faster, and it can travel higher, because the higher we go is part of physics thing. We have less amount of air resistance. So that's why most of the airplanes fight, or the jet planes actually. Say we see these sort of planes. Normally we use it for the warfares. It goes very fast, supersonic speed. It goes at the speed of sound, which is quite 332 meter per second in our regular life. Yeah, it depends, because in air it is 332 or 320, something like that. In the liquid or in hard metals, it goes much faster. It travels faster. So it's a supersonic speed, we say, because it goes at the speed of sound. By the way, speed of light is pretty important in physics. It's 3 into 10 to the power 8 meter per second, which means 8 zeros after 3. Quite much. 3, almost 300,000 or million. Not million, actually, more than billion, sort of. 3 in 10 power 8 meter per second. It's the speed of light, which is important for us because that's how sunlight comes to our Earth. It takes 8 minutes and 20 seconds to reach our Earth, and it also travels the same speed, and it does travel those distances for other planets. That's why the Earth gets benefits than the further planets, and the other planets are much closer than Earth to the sun does get much hotter. So the condition over there is too hot. So everyone knows about it. There's no point of talking about it much. Main point is the laws of physics for aerodynamics and aviation and the plane and the jet tech. Sometimes it needs to go much. It has to take a stealth mode. When we are in the warfare, we have to take the stealth mode. Why? Because we don't want to get seen everywhere. It does have to keep a soundproof system. So, soundproof system for them and the silent system. So, sound doesn't reach anyone. How is it possible? It's possible by going higher than the supersonic speed. Sometimes you won't even be able to realize if you are just a normal plane, unless you have technology to detect that. Comes up. Tumbling is pretty easy, nothing much to learn about, and we wanted to keep our results short for today's lesson. So we're not gonna go further, or we can go further. There are lots lots of things to learn and to convert and to use the laws of physics. That's how we're going to be able to create fridge. We're going to be able to create the heat machines, heat pumps, air cooler, heaters. And that's how the air conditioners work. That's how the factory does work with the heat options. It's pretty easy for us and pretty basic rules, so nothing much to think. The things we're going to talk about: workforce and energy, pretty important. Not pretty much. If I want to talk about thermodynamics, I could go much longer. Pretty easy. But I was trying to make it a little bit interesting. I already took good amount of time while doing it. I have to keep it shorter. So, lots of topics to cover. Work, force. Force was probably a different part that we took. Okay, normally we say work and energy. Force comes up. Force came up. How the workforce and energy comes. So, what is work in physics? When we put some force into something and the object we put the force into did travel some distance, say x meter distance, we call it s. The distance traveled, say the distance traveled is s, and the force we put is F. Then the work done by the force is F multiplied by S. If its direction is, say, with theta degree angle of the force was put in x-axis and the object moved in an angle from x-axis, then the equation goes cos theta multiplied cos theta. And sine cos pretty easy, math, everyone has the basics of it. Fs cos theta. So, in physics, what it means, if we put a lot of pressure and the object don't move, and say one object is not moving, it didn't move at all, then we did put a lot of force, we did burn calories, but we didn't work. In terms of working, we have to make the object move to a certain distance. If it's not moved, no. What happened inside that object? Probably the particles moved or something, because we put a lot of energy. Say heat. We put heat. Say we put some heating pump. Some way, say through fire or some electric heater. We heated some object. So inside the molecules, the atoms did move a lot. But the object, what happened to it? The object expanded. That's another part of thermodynamics or another part of physics. When we put heat to something, normally the objects expand. Say it's a solid material. So through an electric heater, we give minimum, say 10, 20 degree or 20 Kelvin. We increase the temperature, and then the object would extend a little bit. That's why we have to keep a lot of things in a certain position so it doesn't extend that much during extreme temperature. It doesn't happen, but yeah. So what happens? Through the heat, the objects do expand. And that's why. What happens? So internally, the objects. So let's get a little bit into atoms. Atoms are 3D. So we are made, everything in the universe are made of atoms. What are atoms? So there is something in the middle. And then things round up. So atom is a 3D thing. Normally we see 2D pictures. This is a 2D photo, but it's a 3D thing. That's why I painted. So there are orbitals. Say we talk about solar system. This is the sun. So normally we might think, okay, all the solar planets do rotate like this. It's not circle ever, it's ellipse. It's elliptical movement. But the planets do not, it's another part of physics, the planets do never move around the sun like this. Why? Because when we come closer, there are other laws for it. Say there are Kepler or a few other laws we have. When we are, so this is sun, the planets are literally doing the rotating around the sun like this, not like this. The sun doesn't stay in the middle. The sun stays like at a side, and at some points the planet comes closer to sun, and when it comes closer to sun, from this distance to this distance, much faster. Why? Because it's just say we are playing some yo-yo, or say we are playing a spinner or something, we are rotating something. When we have short distance, it does rotate very fast, but when we have long distance, it does rotate slowly. It's the same for the solar system. So we can call it, there's another motion completely dependent on it. That motion is the circular motion, elliptical motion, and there's something comes up, torque. So this is tau. We normally say tau equals I alpha. Alpha is the rotating angle in circular motions, and I is the inertia of the material. So it's the same as mass used in normal linear system. We have two systems we use in our day-to-day motions. One is linear, which is the simplest form of it. Nothing interesting, nothing hard. The circular motion, because we are going around, then what's happening? There are two forces working on it. So, say, when a ball is spinning around a circle, a point, it has two motions. One is towards, mostly it's going towards, so the perpendicular motion towards the thread is, say we put a ball into a thread and we are rotating it in a circle. So if it's with thread, it goes, the direction is perpendicular to the thread, but there are two forces. One force is trying to take it out. The ball is trying to get out of the circular path, and one, the rope is pulling it. So it does not go out and it doesn't come in. What it does is just keep moving around in a circle. So centripetal and centrifugal. This is centrifugal, CF force when it goes out, centripetal when it's attracted towards the central. So pretty easy. What happens in this term? So circular motion, so the torque, inertia we were talking about. Inertia is something that is counted. We do care about it for the motions of circular. If the motion is not circular, if the motion is linear, we just count very easy options like mass. Same thing, just inertia in circular things. So tau is a force a circular object is feeling towards the center. Normally, the laws of physics, we were about to come to the part of force. We were discussing work, force, and energy. We haven't discussed much about work and energy. What is energy? Energy is a thing that transforms from one part to another. Say if it's heat, it can transform itself into electric, sometimes possible. Electric can transform into heat, and sound can transform into heat in some way. Motion, the kinetic energy, can transform itself into heat, sound, electricity, and light, and few other energies. Energies are everywhere. So pretty important and simplest form you could ever see. Force, on the other term, also very simple and easy. But we have to study a little bit. 3 laws of force. We know about. First law, if an object in the universe do not feel any force, then the still object stays still and the moving objects keeps moving. Newton's first law, everyone knows about it. 3 laws, first law, second law, and third law. So the second law is quite much of the demonstration of force equals mass into acceleration. Quite simple, nothing rocket science. It's pretty simple. Rocket science very interesting, by the way. We do develop a lot of tech, and that's where we can't actually unlock huge potential. That comes later after we master our day-to-day things. Rocket is pretty easy. Rocket science is also pretty easy, so nothing much about it. We talk about it soon. We just do propulsion and we go up, and someday we're going to be looking for some more cost-effective. That's very important. Right now it's very much not effective. We are looking for new options that makes it easier and much simpler and easier form of energy, because what we burn or we transform energy into kinetic energy. We need a huge amount of force. So that's what we're working on. That comes at some points. We're going to talk about it. The topic we were in, let's come back to it. We were talking about the first law, that in the universe, if a ball keeps moving, it never does stop. In our world, we have gravity. So the gravity pulls it back. That's where the gravitational forces comes up. Boy, the gravitational force makes a fundamental part of our world. Because otherwise, why can't we go to space? Because the gravity pulls us. Even though we had gone to space, we do not have oxygen, or we don't have enough materials to get back. Unless we're prepared. Otherwise, this is a thing that keeps us pulled towards our Earth. So, a loss of laws and energies and studies regarding gravitation. So, just to brainstorm, just to think about it. G equals m1, m2, say not G. G is a constant, gravitational constant. Say F. I say F prime because it's a force towards any 2 objects. For any 2 objects in the universe, divided by r squared. G is a gravitational constant, which is 6.673 into 10 power minus 11 Newton meter square. Newton per meter square. Into kg. I forgot some, yes. So this is a very universal constant. So what happens? M1 into M2, we multiply the mass and divide by the distance squared. And multiply the constant, we know any force that's been happening is x object of heat. So the universe is pretty big. Alright, we do not know how big it is. Probably it's expanding, probably it's in a constant position, or probably it's super expanding. Right now, the most possible answer is it's expanding, but we do not know the ratio of expansion, if it's gonna keep expanding or if it's gonna stop. So whatever it is, whatever the size is, so if it's expanding, everything's going to follow. Some x object in x position, y object in y position, it does have force towards each other. And how does it work? Towards this, it works easily with this rule. It just, they have mass, they have distance, the force, amount of force pretty low. It's like as low as we can count as almost nothing, but it does have force. Interesting enough.